Hello everyone, my name is Pedro, and together with Sagnik, we are going to present to you our work on Temporal Self-Attention Network, that is an approach to medical concept embedding. The paper that we used considered multidimensional EHR dataset, which basically consists of datasets that have multiple variables from a certain patient. We would have demographic, diagnosis, medication, and treatment data, for instance. And with this diversity of data sources, we ask ourselves, how do we embed this data set? So how do we extract features and also consider a temporal relationship between those variables to understand better the patients and develop machine learning or data insights with it? A first approach would be one-hot embedding, which brings some challenges. The first one is that this would lead to a high-dimensional and really sparse data set. It would lack semantic relationship between those diagnoses, for instance, and would have a poor generalization, which is something that we do not want. Another option would be text-based embedding, which would capture semantic relationships, so this is good. Would also lead to a low dimensional vector, which is also good. But we would lost a little bit of the structure in the AHR data, and we wouldn't have so much temporal relationship between those things. So a better approach would be using a temporal self-attention, which would bring us temporal awareness, would also have contextual and hierarchical fusion, would be lightweight and interpretable, which is really good to understand the relationship between things and understand what the models are thinking about the data, and would have a superior performance than the other ways. So this would be the right choice. And with this, the authors propose a TeSAN architecture, which basically consists of an input layer with codes and timestamps that will lead to dense embeddings. Those embeddings would pass through self-attention mechanism and time gaps to bring context aware. We would also use pooling, leading us to key concepts. And then we would have a final prediction, which could be like mortality risk or even a concept in a timestamp. So unlike simple different embeddings, the idea of TeSAN is that we understand the unity between time and context, which would be similar to a doctor interpreting the patient history, which would be really good.
Thanks, Pedro. For the purpose of our experimentation, we have selected Mimic 3 datasets. It offers high number of records, which is ideal for any machine learning or deep learning model testing. The incidence rate of this dataset is also high at 12.5%, which makes it an overall well-balanced dataset. For the purpose of comparison, we have selected certain baseline models. In the results in the following slide, we'll be comparing the proposed TeSAN model against these baseline models. From the traditional award embedding models, we have CBOW, SkipGram, and GLOVE. We also have specific medical domain-related embedding models, which are Med2Vec and MC. From the following slide, we will be deep diving on the results. So the first test that we have done is on the ablation study. TeSAN model is a complex architecture. There are different layers to it. Ablation study helps us isolate each layer and compare the effect of each layer or find the impact of each layer on the overall performance. So from the results, we can clearly see TeSAN with the full model architecture performs much better than the other ablation variants, which are created by removing certain layers out of the model. Right. So in the following results as well, we will continue exploring the TeSAN full model architecture. Next is trying to understand what is the classification performance out of the TeSAN model. For classification in the Mimic3 dataset, we have a binary variable, which basically indicates the patient expired or survived. We'll be using this label to come up with the classification performances. For the comparison of classification performance, we are comparing with the baseline models. Here also, we see that the TeSAN full model has outperformed the baseline models, right? So clearly, TeSAN is the choice and the overall winner out of this results and comparison. The natural question is that is TeSAN the best choice for any performance, and are there actually any limitations to this model or not? So one of the key limitations that we saw during our training exercise was that TeSAN models were taking very high amount of time to train. It was around 7 times more time to train and GPU requirements compared to the other baseline counterparts. Thank you so much for your time. For any further clarifications, please reach out to us or feel free to explore our GitHub repo.